So let's say that we want to store a key value pair. Okay, so it might be, let's say the key is Riddhi and the value, let's say, is 6, because the length of this string or the length of my name is 6. Okay, now let's say there is another string or name Ashok. So Ashok is the key, right, and the value is 5, because the length of the string Ashok is 5. Okay, also let's say we want to store the frequencies of a number. Let's say there is an array 2 3 5 5 6 1. So we want to store something like this, that 2 comes only once, 3 comes only once, 5 comes twice, 6 comes once, and 1 comes once. So these part, the left hand part, are the keys, right, and these are the values. Makes sense, right? So basically, for let's say if you now want to say that, hey, give me the frequency of 5, so you would search out for 5 and you would find that the value is 2. Now without a hash map, forget about hash maps, how would you implement this? So the basic idea that comes to my mind is maintaining a list of pairs, right? I'm talking in Java terms, but don't worry, even if you don't know Java, you still should know the internal implementation of the hash maps. And first I'm going to talk about the algorithm and the intuition and motivation behind coming up with that, with this hash map, so we would be obviously able to follow. So now let's come back to a question, that how would you maintain such a data structure, right? Or how would you solve this problem? Okay, so you would be basically maintain a list of pairs, and let's say this pairs, or maybe you can create your own class, let's say a class pair, right, where basically you will store, let's say, int key, right, and int value, right? So whenever you want to add a new pair to this list, right, you will simply add it, right? So let's say this list contains 2 1, also it contains 3 2, right, also this contains 5 2. What does this signify? That this is the key and this is the value, right? So it signifies that 2 comes only once, 3 comes twice, and 5 comes twice, right? Now let's say you want to insert a new key value pair to this list. So what you have to do is you will insert it at the end. Make sense? Okay, so let's say you want to insert 6 1. Now query through this list and ask that, hey, what is the value of 5, right, or how many times 5 comes, right? So for that we have to traverse through this list and find out that, hey, the value of 5 is 2, right? So basically you will traverse this list, you will check that whether this key is equal to that particular key, that is the current index, and if there is a key match, you would return the value. So that's the basic idea we would come up with, right? Now what is the time complexity for this? To find a key, or to find a value to its corresponding key, what is the time complexity for this? The time complexity is obviously O of n, that is where n is the number of entries in this list, right? Because in worst case you might have to traverse the entire list to find the key and hence its corresponding value. Can we do better, right? Can we do this in some constant time? And that's where HashMap comes into the picture. But still we are far away from HashMap. We will slowly build up a solution towards HashMap. Let's see, can we better it up? And let's only focus on this problem, that is calculate frequency of an array of integers. Okay, so now obviously we can't do this, we need something in constant time. So in order to do this, what we do is we create an array, right? So this array will obviously have some indexes, right, 0 3 4 5 6 7 and so on. Okay, now let's say we are given this array, right? This is the input array 2 3 5 5 6 1. Let's write it down, or let's maybe change this array a little bit, 2 3 5 5 6 1 3, right? So what we will do is, whenever we find 2, we would go to this index 2, right? Initially this array will all have zeros, right? Let's say everything has 0, right? Because yeah, I mean that's the default value, right, in Java. So now 2 comes, we will go to this index 2, we will increase this value to 1. 3 comes, we will go to this index 3, we will increase this value to 1. Similarly for 5, we first increase this value to 1, then again 5 comes, so we increment this value to 2, right? 6 comes, we go to index 6, we increment this value to 1, then 1 comes, we go to this, we increment this value by 1, we again come across 3, right? We go to index 3 and increment this value to 2. So at the end our array looks like 0 1 1 2 0 2 1 0, and the index is 0 1 2 3 4 5 6 and 7, right? So now we know that hey, 1 comes once, 2 comes once, 3 comes twice, 5 comes twice, 6 comes once, right? So here, in order to insert an element, right, or we took O1 time, right? But now let's say we want to query this array. We want to say, hey man, what is the frequency of 5, right? We will straight away return AR of 5. That will give us the frequency, right? Here we don't need to traverse to this list to find out what is the frequency of 5. We will simply go to the index, right? Because we know if an element 5 came as a key, we would have gone to that index and incremented the value, right? Similarly, if we want to find a value corresponding to a key, we will simply go to AR of key and we'll return that value. Make sense? So this takes O1 time because we know indexing an array element is O of 1. But there is a problem. What should be the size of this array? Can we know it? Yeah, we can know it if we say ki, okay, tell me that what is the maximum number that can be given as an input element in that particular array. Since we are kind of whatever element is coming, we are going to that particular element in this particular array, right? So in order to know the size, this maximum size can be the maximum element in this array, right? Makes sense? But let's say this maximum element can be huge, right? So for example, let's say this array contains 5 elements. The input array contains 5 elements, 0, 1, 10 to the power 5, 3 and 6, right? Something like that. So just for maintaining 5 elements, we have to create a massive array of 10 to the power 5 to maintain our frequencies. Isn't this an overkill? There's 5 input elements, but this frequency array that we have to create, this auxiliary array that we have to create, that is 10 to the power 5 because the maximum element in this array is input array is 10 to the power 5, right? And if we don't create a size of 10 to the power 5, there will be no index of 10 to the power 5, which will give an array index out of bounds exception. So this is an overkill, right? But it's a good start. We actually understood that, okay, this can be done in O of 1, right, in terms of time, but the space is a little bit of factor. It's a lot of overkill that we're doing. So can we improve it? And that's what we're going to look here. Okay, so far what we are doing, there was this key, right? And this key was mapping to some index in our frequency array, right? So let's say 5 came. So let's say if 5 came, if key was 5, we said, okay, map it to index 5. If key was 5, we said map it to index 5. Now, can we improve it a bit? Because we want to save a little bit of space. So before doing that, let's give a generic name to this array that we were creating to store the frequencies, and we will call it a bucket array. And we're going to use this term a lot as we go along in the video. Now, let's say instead of creating and depending on the maximum element that can be present in that array, let's create this bucket array with some size initially, right? With some size of, let's say, 20. Let's just create this bucket array. Okay. So this bucket array will have a size of 20 initially. Okay. It can be anything. You can like create with a 10, 5, whatever you want to, right? Now, let's say a key comes, right? And what are the operations? First of all, also we have to understand what are the operations we want to do, right? We can insert a key value pair, right? We can remove a key value pair, and we want to query or find a value for a key. That's what we want to do, be it finding out the length of a string or length of a name, or be it finding the frequency of a particular integer. So initially, let's say that we will create a bucket array of any size, let's say 20, right? Now, how would we insert a key, right? So to insert a key, we have to find the index in that bucket array in which that particular key will go, right? So what we'll do is, we need to convert this key into some index. So let's say if it is 5, okay, then to we were saying ki, hey, just go to index 5, right? It's already an integer, right? But let's say if it is Riddhi, how can you convert this string into an integer, right? Or let's say there is, instead of a string, we are using some custom object like a student or an employee. In that case, how would you convert it to an integer? Because an array index will always be an integer, right? So we have to convert whatever key is there to some integer, right? So we do that using a hash function. So basically what we do is, we take this key, we pass it to some hash function, and this hash function gives us the index in which that particular element should go in this bucket array. Make sense? Now what does this hash function comprises of? One is the hash code, right? What is this hash code? This hash code is nothing but an integer value. So let's say you have a string, okay, let's say Riddhi, and you pass it to some hash function. So it generates an integer, right? Let's say it generates an integer of 23. Okay. Let's say there's another string ABC, and you pass it to some hash function and gives you hash code of 40 or 409, something like that, right? Because hash function, what it is doing, it is just converting an object to some integer value, right? But still there's a problem. How are you sure that this 23 or this 409 index will be present in your bucket array, that is this array? It might be more than the size of the bucket array, because the integer that is coming out to be, that can be more than the size of the bucket, because this hash function doesn't know what is the size of this particular array is. For now, don't think too much about hash function and what it is and how it can be. Just think of it as a magic black box, where if you pass any object, that hash function will convert it to some integer value. That's it, right? And we need that integer value because we need to map it to the bucket array. We need that index, right? But also there's a problem. So this hash function gives us a hash code, right? That is 23 for ABC. Let's say it's 409. But it might happen that 409 is not present in the bucket array. Just consider this case, na? Let's say this bucket array has size 20, and Riddhi's hash code comes out to be 23. ABC's hash code comes out to be 409. And none of these two indexes are present in this bucket array because it is of size 20. So it will only have index from 0 to 19. So what can be done? So there comes a compression function. What is a compression function? That compresses your integer value to such an integer such that it lies within the range of your bucket size. Very complex, right? Let me simplify it. It is nothing but simply doing hash code mod your bucket size. That's it. So if your bucket size is 20, your 23 will come out to 23 mod 20, that is 3. So it will go to index 3 of your bucket array, and if ABC is 409, so it will simply do 409 mod 20, which is probably 9, and that means that ABC will now point out to 9th index of your bucket array. As simple as that. Okay, nothing fancy. So what is happening? Any object, be it string, be it integer, be it a student, be it an employee, any object, right? Which is the key? It comes, passes to some hash function, generates a hash code, then again you pass it to a compression function, which is nothing but mod the bucket size, and you get what? You get the index of the bucket array, right, where you ideally want to put your key in, right? Now let's say if you want to find a value for the key, what you would do, right? So let's say you inserted Riddhi, and Riddhi is inserted, and it was inserted at index 3. Now let's say you are saying, okay, give me the value back for Riddhi. Let's say for Riddhi, the value you inserted was 6, right? It ideally means that at index 3 in this bucket array, 0, 1, 2, 3, Riddhi, 6 resides, because that is a value, right? Now, if you want to fetch the value of Riddhi, what you would do? You will again pass it to the hash function. It will get you the hash code 23. Remember, the hash function needs to be consistent. That means that first time you run Riddhi, it gives you 23. Second time you again pass Riddhi to that hash function, it gives you 403. That is not going to work. Every time your hash function should be such that it gives you a consistent value for the same key, right? Or the consistent hash code for the same key. So again, if you pass Riddhi to this hash function, it will give you the hash code 23, and you do a mod of bucket size, which is mod 20, and it will give you 3. You go to this index 3 and you find the value 6 and return the value 6. So in this way you can insert, you can delete, right? Similarly, remove is also something you can do like this. Basically, you find the index of that particular key and you delete the value. That's it. It works. Okay. Now let's talk a little bit about the magic part, that is the hash function. So now what we can do is we can say, hey, for an integer value, right? Let's say 5. Now for this hash function, we can just say return 5. For 6, we can just say return 6. That's fine. I mean, we can do that. That's not a big issue. That means whatever value, so basically, let's say this is an int hash function. This is a function, let's say, and we are passing some integer value. So we can just say return a only, right? So whatever value we are passing, just return that, right? And that's what we are doing when we were finding the frequency of the numbers, right? What we were doing, just imagine like this, a number 5 comes. What we were doing, we were inserting it in 5th index of the array. That means what was happening, the element or the key was pointing directly to the index in the bucket array. This is simply that, right? But what if Riddhi comes in? Can you directly do this? No, right? You can't return a string because you have to return an integer. So in that case, one of the things what you can do is you can just sum up the ASCII values of each of these characters, because ASCII values can be basically integers, so you can just return sum of ASCII characters, right? But there's a problem. What if there is a string DDHIRI, right? Or let's say there's a string IHRDDI. Basically what I'm trying to say, you just permute this string, right? You have different permutations of the string, and all of them will have the same sum of ASCII values. That means all of them will result in the same hash code, and as a result all of them will point to the same index of the bucket array. What I'm trying to say again is, let's say of this bucket array, right, of some size, let's say 20. So this is the bucket array. Okay, so now this string comes in, sum of ASCII, let's say, comes out to be something, right? So what we are doing, this key comes, passes to an hash function which is sum of ASCII, right? That is like, let's say that is of some value, let's say 23, let's say, and the bucket size is 20, so it comes, the index comes out to be 3, right? So at third index, right, Riddhi, so the value of Riddhi, that is 6, is being inserted, right? Now again, let's say this comes, right, and its value, let's say the value, this is the key, the value which you want to insert is, let's say 15, and the value which you want to insert is 23, right? Or let's say 20 to 30, right? This is the value, right? This is the key, don't confuse. Okay, so now DDHIR, it passes to the hash function, since it is also sum of ASCII, right? It will give you the same hash code 23, right? Because since it's a permutation of the same string, it is like, the ASCII, some of the ASCIIs will be the same. Think about it. And hence the bucket size mod 20 will again come out to be 3. So now what we have is a hash collision. That means in the same index in the bucket array, multiple keys are trying to enter. So now Riddhi was already present in this spot. Now DDHR string also wants to come to this index 3, because the hash function was written in such a way that for different keys you are getting the same index, you are getting the same values. So your hash function was not able to uniformly distribute the values, right? So that is why it is very important to have good hash functions, so that the values or the indexes in this case comes out to be uniformly distributed, so that you can minimize the hash collisions. Now why do I use the term minimize? It's because even after doing a lot of things, there will still be hash collisions. You just can't get away with that fact. But the idea is to come up with a better hash function, right? So that these collisions can be as much as possible avoided. So here we understood that why do we need good hash function, so that we avoid these collisions. So now your question might be, how can I come up with good hash functions? What you can generally do is you can there's a hash code functions in object class, which basically gives you the memory address of that particular object. So you can simply use that, like you can simply use that hash code method of the object class, which we are going to see that in action when we would be coding, right? And you can use that, right? But again, like you really don't need to worry much about a good hash function, because there is a lot of research that goes on about it, right? It is also use case dependent at times. So for now, don't think of it as much, right? And just think of it as a magic box. And for the internal implementation part, what we are going to do is we are going to use the hash code function, which is already implemented in the object class, which basically gives the memory address of that object, right? So that is what we're going to do. But let's say we have a good hash function in place, but still we come up with this problem. That means in a particular index, multiple keys try to enter, right? So there's a problem of hash collision. And now the question is, how can we deal with hash collisions? Well, as it turns out, there are two ways to deal with hash collision. One is closed hashing or separate chaining, and another is open addressing. First, I'm going to talk about the closed hashing or the separate chaining, and then we're going to see open addressing. So what happens in a closed hashing? So let's say we have this bucket array, okay, and let's say it has some size, so on 20. At 3 index, there is already a value present, that is 6. Now there's some another key who also wants to come to this index. So what do we do? So the idea is, in this bucket array, instead of storing one value in one index, in a particular index, store a list of values. So every index in turn will be a list of values. So ideally what will happen is, let's say this 3, let's say this index is 3 and there's a value 6 that already exists. Next time if another key wants to get inserted into this index, it will just take up the next position in this list, right? So let's say 5. So what I'm trying to say is, every index of this bucket array will be the head of a linked list. So ideally all of these things will be clear when we'll be coding this out. So ideally what is happening is, this bucket array is an list of head of linked lists, right? So every index in this bucket array will point to the head of a linked list. So what is happening is, let's say at 3 is what? A head of a linked list, right? And initially it is empty. So the first, let's say at position 3, some key wants to come. So that is that key is now the head of the linked list, right? So let's say at 1, right? There is no element at position 1. So head is null. So now at 1, let's say a key value pair comes, let's say Riddhi R, and its value is 5, right? So then it is like inserted as a first element in this linked list, which is pointed by 1, right? 1th index. And next again some value wants to come, once again some entry key value pair wants to come again. So what we'll do is, we will add another element to this linked list, and this one will point to this particular element. These things will get more clear, but you can, for now, what you can think of is, every index in this bucket array will point to a linked list, or will point to the head of a linked list, right? So in this way what we do is, we deal with the hash collision. Now what is open addressing? So open addressing is all about, if there is a hash collision in particular index, find some alternative index, right? And there are different functions to find the alternative index. There is something called linear probing, right? Then there is something called quadratic probing, right? Then there is also something called, double hashing, where you like have 2 hash functions, right? But in practice, separate chaining works really well and works almost similarly to open addressing in most of the cases, and it's very easy to implement. And also in Java, the internal implementation is separate chaining, closed. So that's why I'm not going to delve too much into open addressing, otherwise it will be a huge digression, and we are going to stick and understand the internal implementation of HashMap using closed hashing and separate chaining. Okay, that's enough theory for now. Let's quickly jump to the coding part of this video, and we will see what are some of the important concepts that are still left. So yeah, let's first jump to a little bit of code. Try to implement what all we have discussed, and then we will see what are the things that are left. So now let's jump to the coding walkthrough, and I would explain you the challenges, right? Some of the important edge cases that you should not miss while coding out, and also apart from that, I will be giving you a step-by-step walkthrough to the code. Cool. So I have 2 classes. One is our map test. So this is just to test out our map, right? So what we will do is, we will create our own map, and this is nothing. This is just a generic type that we are passing, where this is the key and this is the value. We are creating our own map, and we are putting some values, right? And we are simply getting the values for these corresponding keys. So nothing fancy in this, okay? Now I've also created my class, that is our own HashMap, right? Where basically these 2 are generic types. This means that there will be 2 user defined types that will be passed to this class at runtime, and this K means the type of our key, and this V means the type of our value. So this map should ideally contains 2 things. One is the key, which should be of type K, and one is the value, which is of type V, and that type would be defined by the users, right? So here you can see it is defined by the users, where K is the integer and the string is the value. Okay, so what should our map now contain? That's the first thing. What is our map internally? We just saw it is nothing but a bucket array, right? And what is a bucket array? It is basically a list of linked list, where each index of that list, right, or each index of that array is pointing to the head of a linked list, right? So I will simply paste this, where I create a private member which is basically a list of this map node, right? And we call it bucket. Now what is this map node? It is not created anywhere. So this is a class which I'm going to talk about and create, and this is nothing but the node of a linked list, right? That's what we are calling map node, and this is KV because we are going to store the key value pair as I just mentioned. So we are going to so the key value pair would be stored in that node, right? So in that map node, that is each node of a linked list that we would be maintaining. So let's quickly see that what is a map node. Okay, so I just pasted this map node class, right? So this is a private class and it's an inner class to this our map, because this map node has no existence outside our map, right? So outside this class, outside this main map class, this map node has no existence, and also I don't want this map node, because since it's an internal implementation of our map, I don't want it to be exposed to other outside world, right? So that is why I've created a private class inside our map class, okay? And this contains the key, it stores the value, and it also stores the next, right? The next as in that, as you know, as in a linked list we store the next pointers, right? Also I could have implemented a double-ended linked list as well. Usually double-ended linked lists are implemented, but here I am going, just to make things simple for you guys, I'm creating a single linked list over here, single linked list. If you want to implement it on your own, you can use a double-ended linked list, because in Java that's the way it is usually implemented. Okay, and this is a constructor which takes the key and which takes the value. Okay, so this is just our map node class, and our map will basically be a list of this map node, that is the list of the linked list, and this we call the bucket. Now there are a couple of other things a map will contain. One is the capacity, right? Capacity as in the size of the bucket. This size, so this is basically the length of the bucket, right? This is the number of elements. This size denotes the number of elements in the map, or number of entries in the map, or number of key value pairs in the map. And this initial capacity is nothing but the initial length of the bucket array, and this is something you can either pass on your own, user defined, or we can have some initial capacity, right? So now let's take a look at the constructor of our map class. So whenever someone instantiates our map class like this over here, what happens behind the scenes is this bucket array is being instantiated, right? And this capacity of this bucket array is set to the initial capacity, right? Then we traverse to this capacity, that is the length of this bucket array, and we insert null. Yeah, this is a very important step, don't miss this step. Okay, so why are we doing this, right? Why we are doing bucket.add null, right? See, you said your bucket size is, let's say, 5, right? Initial capacity is 5, but since it's a list, if you're not adding elements to that list, this list in Java is ideally still size 0, because I have not added anything to this list. Now you want to insert an entry where there is some particular key, and this key goes to some hash function first, right? And then it goes to the compression function, and the compression function says, hey, the bucket size is 5, so let me find an index between 0 and 4, right? So this key now ideally wants to go between 0 to 4, and let's say it comes out, it wants to go to index 2. Based on the hash function, it wants to go to index 2. And since you have set the initial capacity to bucket size as 5, right, it should ideally expect to find 2, but hey, the list is of size 0. Then where will it go? It will give you an array index of bounds exception. That is why it is important that you do this line, basically you do bucket.add null, so that at least you ensure that that index exists. Whatever initial capacity you have, those capacities or those indexes exist, and that is why I'm adding null values. If you miss this step, you will run into error, right? Also, the reason is you're using a list here and not an array. If you would have been using an array, right, this problem would have been solved, right? Because an array, whenever you're creating an array, you have to give the predefined size, and then you know that anyway that index would be there. But in list, it doesn't happen like that, right? In list, it's dynamic. Like whenever you push an element, then only the list size increases. Here we are using a list, not an array, because we are dealing with generic types, right? But you're not using array because you're dealing with generic types, so you won't be able to instantiate it. Comment down below if you've understood it. I'm not going to dive too much deep into it. I'm leaving up to you that why you can't use arrays, and if you can, what would be the right way of doing it. But here I'm going with an easy technique of using a list. Okay, so this is a very important step, guys. As I told, that you have to follow this step, right, if you're using a list. Okay, we are set up. Now we want to implement our get function. So basically your get function, what it should do is, it should take the key, right, of type k, and it will return me the value for that particular key. If it is not able to find the value for the particular key, it will return null. Okay, what is the other function? Other function is putting value, right? So let's say I want to, for a particular key, right, I try to put a particular value. Now what if that particular key already exists? Like let's say for key 5, I have a value that exists, that is 3, right? Now again I'm trying to insert 5 comma 2. That means for key 2 I want to insert the value 2, right? But the key 5 already exists. That means I would simply do an updation. So now previously the key value pair was 5 3. Now it will be updated to 5 2, right? Now another function which we require is removing a particular entry for that particular key. So these are the 3 functions which we are going to implement. Okay. So now let's try to implement the get function. Okay. So for finding out that whether a particular value exists for a key or not, and whether what is that particular value and return it. So what we have to do? We have to find out the index in that bucket array where that key resides, right? And how can we do that? We can do that with the help of our hash function. So basically we will get the bucket index by a function, let's say that is the hash function, where we will pass the key, and that key will give us the bucket index where our key might reside. Okay. So what is this get bucket index? This is basically the hash function which will comprise of 2 parts, getting the hash code as well as using the compression function to make it within the range of the bucket size. Now let's see what this bucket index function looks like. So this is nothing but it is doing key.hashcode, and where this key .hashcode function comes from. So every object in Java has its parent as object class, and in the object class, as I told you, there is already a function implemented, hashcode, right? So therefore, which is basically the memory address of that object. So therefore we can get the hash code by using this key.hashcode function, and then we simply mod it by capacity as the compression function to map it to the index within the bucket array, right? So this is nothing but getting the bucket index where your key might potentially reside. Okay. Now why am I saying potentially reside? It's because let's say that key is not there, then what happens? You will return a null, right? But you still have to go to that particular index and traverse the linked list to find out, right? So that is why I'm saying potentially. You know that if your key would be there, it would be there in that particular index only. If this would have been inserted, it would have been inserted in that particular index only, right? Now what is the next step? You've got the bucket index, right, where your key might reside. Now the second part is to get the head of the linked list in that index, right? And that's what we do. We get the head by saying bucket.get bucket index. So now we are traversing to the end of the linked list, and what we would do is we would check that if head.key, right, if this head.key is equals to the key which you are trying to find, then simply return this value, right, of that particular node. Otherwise go ahead and do head.next, and if we come out of this loop, that means we have not found our key, that means that key doesn't exist, and we return null. Make sense? Now there's one slight problem. We are using this equality operator, right, to compare these two values whether they're equal or not. But in Java we know, since what is this head? This is an object, right? And what is this head.key? This key is of type k, right? And k is an object, because every generic type in Java is an object. Even if it is an integer, it will be converted to its corresponding wrapper class. We have saw that in the collections video, right? In my collection framework video, please go and check it out if you haven't. So there I discussed that every generic type is of type object, right? And that is why if you're simply doing the double equals to, right, equals to operator, it will be just comparing the memory address of these two values, not the actual values. Also think in this way. Let's say for integer it's fine. Let's say for a custom object, for example student. So if this key is of type student, right, then you can't compare two custom objects using to equal operator, right? You know that. In Java you can't do that. It will be simply comparing the memory address but not the actual values. So for that what we use? For that we use the equals method. Every object has that equals method, right? You can override it as well for your custom object. So now can you understand, for your custom object to be used by HashMap or to be able to be used by HashMap, you need to implement the equals method and you need to implement the hashcode method. Now do you get it? Why I told in the collections video, if you have watched the collection framework video, why I told you in that video that hey, you need, whenever you're using a custom object, right, and you want it to use in your HashMaps, you need to implement the hashcode method and you need to implement in your equals method. Otherwise your HashMap, right, won't give you the correct results for your particular object, because it depends on the hash code as well as the equals method. This is a very important question. This is a very important question. In a lot of interviews they would ask you that hey, like what do you need to take care so that you can implement it in a HashMap, or maybe why is it important to override the equals and the hashcode method? Can you just do away with implementing just one method and stuff like that, right? You need to implement both the methods. For not custom objects, let's say for objects that are there which you are not customly building, For that, the equals and hash code method is anyway like written, so you don't need to take care of it, right? So that is why it's important that you write the equals and the hash code method, okay, for the custom object, and that is why in the collections video I told you about this. Cool. So this was all about the get method. So you get the bucket index, right? And then you get the head of that bucket index, you traverse till it is not null, you check that whether it is equal to that key, then you return that value, otherwise you keep on traversing and in the end you return null. Now let's look into the put method, right? So put again is very simple. First you have to find out that, hey, where does this key will potentially go, right? What is the index? So again you have to find out that bucket index. So you find out that bucket index, right, using this function, and you get the head of the linked list in that bucket index. Now first of all you have to check that whether that key is already present, because if that key is already present, what you would do? You would just update the value and you don't need to do any insertion of the node, right? You would update the value of the node. But if it is not the case, then you would insert. So we will see, first what you do is you get the bucket index, then you get the head of the linked list in that bucket index, you traverse the head, very similar to get, right? While head not equals to null, right? If your head or key equals key, that means that value is already present, you simply update the value of that node and return. You just don't do anything. Otherwise you keep on traversing, right? And if you reach up this place, that means, hey, you didn't return anything and that your head reached null, that is why you are here at this line, this line, right? That means there is no entry of this particular key, so you have to insert a new entry, you have to insert a new key to your hash map, and that is why you are implementing the size. That means what is size? The size is the number of elements or the number of keys in the hash map, and that is why you are increasing the size. Here you don't need to increase size because your key was already present, you just updated the value, right? So now increase the size of the hash map, and you now need to put your element or the entry or make a new node, and you need to put it inside that bucket. So what we do is we create a new entry by passing the key value. What we do is we get the head of the current bucket again, right? Because this head was exhausted because we traversed to it. Now what we do is we simply add an element to the head of the linked list. That's it. So now what we do is we set the next pointer of the newly created entry to our current head, right? And we set the bucket index to our new entry. That means now the new head of this bucket index at this bucket index is the newly created node that we created, and what we ideally did was we created a new entry and we inserted it to the first of the linked list. You can also choose it to insert at the last of the linked list, that you can also do. I chose to insert it at the head of the linked list. So what we did again was we took got the new head, the current head, right, and we made the new entry point to the current head. So that the current head becomes the second element, and we made the new head as the current newly formed entry or the newly formed key value pair by setting its bucket index to this new entry. Very simple. Okay. Now let's look at the remove function. Now remove function is very simple. For that particular key, right, find out whether it exists in that hash map, right? If it doesn't, then don't do anything. If it exists, then remove it. What do you have to do basically for that? Get the bucket index, right, where that key might reside in, okay? And then once you get that bucket index, there will be a linked list in that bucket index. You get that head in that bucket index, you just traverse to the linked list and remove the node that you have to. Basically the problem boils down to removing a particular node in a linked list based on its key, right? So I will just paste the code. It's very simple. You get the bucket index, you get the head and the priv, right? And the moment you have found the key that you want to remove, that means that is the node you want to remove. So you basically do the same operations that you would do to delete a node at a particular position from a linked list, right, by taking the use of these priv pointers and head pointers, and you decrease the size. That's it. I will leave this code to you because there is nothing related to HashMap. This code is very similar to removing a particular node in a linked list. That's it. So that is why you can pause this video for here if you don't understand it, or let me know in comments and I would explain out to you. Okay. So remove, put and get has been taken care of, and so far let's quickly test our things if it's working. Okay. So let's see, quickly run it. So as you can see, for 5 we get RIDDD, right? That's fine. For 1 we get A, for 6 we get Riddhi, for 3 we get ABC, and since 7 is not present, we get null. Things are perfectly working so far. So let's look at the time complexity of insert, right? So what are we doing in insert? So we are trying to traverse to the linked list to find out whether any key already exists, then we are updating, and if it doesn't, then what happens? Then we insert it to the front of the linked list. So let's say that we have this bucket array. First we use this hash function to find, let's say there's the key, we have this hash function, and we try to find out the particular index, right? And then we traverse to the linked list of this particular index. That's what we are doing, right? So one thing that is involved is finding the hash code. This is constant almost, okay? This is almost constant. I mean, this is not exactly constant, but if you compare it with the the overall complexity, this comes out to be constant. Now two things, one is n, which is number of entries that exist in the hash map, and one is b, that is the number of buckets, or basically the bucket size. That means the length of this array is b, and n is the number of entries in our hash map, right? These are the two values that we would use a lot, right? So now the second thing is traversing to this linked list. Okay, this index is found in constant time, but traversing to this linked list will take some time, right, to insert an element or to find a particular key. Now in worst case, it might happen in one particular index of this bucket array, all of your entries lie. There was hash collision and all of your entries lies in one particular linked list, right, or in one particular index. In that case, and in worst case, you have to insert a particular key, you have to traverse to the entire linked list, right? And all of these n elements are in this particular index. So that means your insert or get condition in worst case can come out to be O of n. That is a possibility. So now how can we get rid of this, and how can we decrease at least our time complexity to constant time as we proposed? So now this happens first of all very regularly, because enough research has been done to find out good hash functions which uniformly distributes the elements. Now when I say uniformly distribute the elements, it means that if the number of entries is n and b is the number of buckets, then at each index the size of the linked list won't be greater than n by b, right? That means the size of the linked list won't be more than n by b. That means at every index there will be not more than n by b entries. This n by b is what we call a load factor, okay? So in order to ensure that this insert and as well as getting of these keys and its corresponding values comes out to be in constant time, we say that this n by b should be less than, so in Java as far as I remember, the value is 0.75, or let's take 0.7 for now, okay? So we must say that, okay, we have to ensure that this n by b value, right, that is the number of entries by the bucket size, should be less than 0.7. In Java, as far as I remember, it's 0.75. You can go and check out the HashMap code. And this is what we call a load factor, okay? So the load factor should be less than 0.7 or 0.75. What happens if it is greater than 0.75? Then we do something what we call as rehashing, which is again a very important concept. So in rehashing, the first step is what we do. We see that, okay, this n by b, this value needs to reduce, right? In order to make this n by b value reduce, what we do is simple numerator denominator logic. We increase the bucket size, because if we increase the bucket size, the n by b value will decrease. So what we do is we double the bucket size. That means if it was 20 previously, now it would be 40, right? And once we increase the bucket size, we rehash the values. That means for every entries in the old bucket list, right, we would rehash and we would put it to new indexes in this new buckets array of doubled size. Now this rehashing, what do you think should be the time complexity? The time complexity should be O of n, because we have to rehash each and every element, because now we have increased the bucket size. So therefore we have to rehash all the elements, right, all the entries that were there in the bucket. So now you will say, hey, to rehash we are taking up O n time. Chill, don't worry. You don't need to do a rehash at very frequent intervals. You will be doing it at very small intervals, right? And hence your average complexity, though in some of the cases where you have to do rehashing, but in average time complexity will still come out to be O of n. Yeah, in worst case it can come out to be O of n for some of the cases where you have to rehash, but in most of the cases it will be O1, and also the average will also come out to be around O of 1. Average will come out to be still constant. Also one more thing you have to notice here. Let's say you have this old bucket array, right? This is the old bucket array and this is the new bucket array of double size, right? So now you can say that, okay, at this index 3 there was some linked list, let's say this, again at this index there was some another linked list. Like instead of rehashing, just blindly copy, like also in this newly formed array of double size, so this 20 if it's 40, we just copy the same linked list, right? And also here we copy the same linked list instead of rehashing all the values. No, that won't work, because try to understand that, let's say there was some object, right, whose hash code was coming out to be, let's say 31, and let's say you had initially your value, your size of the array was in the 10, right? So you would do mod 10 and your index was coming out to be 3. Now there was another object, you pass it some hash function, right? And it was coming out to be 41, okay? And since your size was 10, it was coming out to be 1, right? But now in the new array, let's say you want to get this 41, right? Here to what you will do, here you would simply say, okay, 41 mod 10 is 1, so it was present at 1th index. So here just copy it at the 1th index, right? So 41 will be present at the 1th index. But now since your bucket size is increased to 20, so 41 mod 20 would be 1, that's fine. But what about 31 mod 20? Will it still give 1? It will give 11. In the new bucket array, it will be searching at 11th index, but since you have just copied from the old bucket array, this 11 is present at index 1, right? So that is why simply don't blindly copy from your old bucket array to your new bucket array, instead rehash, because you have to understand your compression function has changed, because now you are doing the modulus using the newly formed bucket array whose size is double as the previous value. So that is why please keep in mind, don't blindly copy and instead rehash all the elements of your hash map. Now we will see the code. Okay, so let's see that how we can modify the code so that we are able to rehash and bring down our time complexity. Okay, so where do you think the change should come? The change should come only in the put function, right? Because when you are removing, there is no need to change, right? Because that is not increasing your number of entries. Only while you are doing put or you are inserting, then it is changing the number of entries, right? So then only you need to check whenever your size is increasing, your number of entries is increasing, then only you have to check the load factor, right? So what we will do is, in our put function, we will go to the last line once we have added all the elements, right? And we will first find out the load factor. Okay, so load factor is 1 into size by capacity, right? And here we are printing out inserting key in load factor, right? Printing out the load factor. Now we are checking if the load factor is greater than 0.7, then we rehash. If it is not greater than 0.7, we don't need to rehash. Okay, now how will we implement the rehash? Let's implement the rehash now. So first we are simply printing that hey, we are rehashing buckets, right? Then we get a temporary variable which is pointing to our old bucket or the current bucket, right? Then we create a new bucket. Basically what we are doing is we are creating a new array list and we are increasing the capacity, we are doubling the capacity, and in that bucket, similarly what we are doing in the constructor, we are adding null. So now our new bucket or the current bucket is basically instantiated and we have taken a copy of the old bucket inside the temp, right? And we have reinitialized our size to 0, right? Because in this new bucket or the current bucket there is no elements. Now what we have to do is we have to rehash all the elements in our old bucket that is there in the temp variable, and we need to rehash them, right, and reinsert them in the new bucket. So what we are doing, we are traversing through this old bucket that is temp, right? We are getting the head of each of these indices. We are traversing through each of this linked list, right? And each of this linked list will be basically a node which will denote a key value pair, and we are simply calling the put function. What this put function will do, basically it will insert this new element, right? This will insert the new element or the new node, right, in our newly formed bucket array, right? And then we will go to the next node and we will again do the same thing. We will put this value, right? And in this way, what we are doing is we are doubling the bucket index, right? We are reinstantiating a new bucket by taking a copy of the bucket, right? And then we are traversing to the old bucket and rehashing and reinserting all the values into the new bucket. That's what we are doing. It's very simple once you go to the code and implement on your own. If you don't implement yourself, it will be tough for you, right? And before rehashing, we have to find out the load factor, and we have to check whether the load factor is greater than 0.7 or not. So we'll just quickly save this code and we'll simply test it out to see if things are working. So you see, first you inserted key 1, the load factor was 0.2, 6, 0.4, inserted key 5 at 0.6, now 3.8, hence you are rehashing the buckets, and now you are inserting 5, your load factor has come down to 0.1 because you have doubled the size, right? And here you can see your results. So yes, that's it for the video, guys. I hope it was insightful. So we learned a lot of things about the internal implementation in the hash map. We also saw the code. We also saw what is hashing collision, what are the two ways of dealing with hash collision. We implemented one of them, separate chaining, right? We also saw rehashing, we also saw the time complexity, a lot of things, and I'm very sure after watching this video, a lot of things about HashMaps would be very, very clear. I hope again this video was insightful, and if it was, please press the like button and subscribe to my channel and press the bell icon, so every time I upload such similar videos you get notified, and also gives me a lot of motivation to make such videos, because these type of videos take a lot of time to make and create. So I really hope that you would keep on supporting my channel like this. That's it for the video, guys. Don't forget to comment down below if you have any doubts, and be more than happy to resolve it. Also, if you find across any such comment or any such doubts where you feel you know the answer, please feel free to jump in if I have not replied yet, and like help that guy out. And thank you so much, guys. I will see you in some other video with some more other similar content. Till then, stay safe and goodbye.